Hi, welcome back to my channel. My name is Gina. In this video, we're going to talk about the improper integrals. Improper or unbounded integrals are definite integrals that cover unbounded area. And there are two types of integral that are considered as improper. The first type is when you have infinite bound. That is in the form of integral of f of x evaluated from a to infinity, or integral of f of x evaluated from negative infinity to b. Here on the graph, I showed an example of the first integral of f of x evaluated from a to infinity. And that is, you want to find the area under the curve f of x from a to infinity. And the second type of improper integral is when you have discontinuity at or within the bounds. And the most common case for this type of improper integral is when you have vertical asymptote at or within the bounds. In this example, the vertical asymptote is at x equals to a, but I want to find integral of f of x evaluated from a to b. That is, I want to find this area here. So again, the area is unbounded. So in this video, we are going to discuss how to evaluate integrals with unbounded area. Let's start with the first type, when you have infinite bound. The approach here is to replace the infinity by some other value, and take the limit as the value goes to infinity. For example, here I have integral of f of x evaluated from a to infinity. But instead of taking the integral from a to infinity, now I'm going to take the integral from a to L. And I'm going to take the limit as L approaches infinity. Using the mathematical notation, it equals to limit as L approaches infinity of the integral f of x evaluated from a to L. And if this limit exists, then this region's sign area is bounded. And when the limit exists, we call that the integral converges. If not, we say the integral diverges. Now let's look at some examples. The first one, we have integral of 1 over x, and the integral is evaluated from 1 to infinity. So we use the approach, we are going to replace the infinity by some other value, and we are going to take the limit of the value, for example L, to infinity. So the limit of the integral 1 over x evaluated from 1 to L, which equals to limit as L approaches infinity of line of L minus line of 1. Line of 1 equals to 0, and the limit as L approaches infinity of line of L equals to infinity. So this integral diverges. Now let's look at the second example. Integral of 1 over x squared plus 1, evaluated from 0 to infinity. We replace the infinity and take the limit as the value L approaches infinity of the integral 1 over x squared plus 1, evaluated from 0 to L, which equals to limit as L approaches infinity of arctan of x evaluated from 0 to L, which equals to limit as L approaches infinity of arctan of L minus arctan of 0. arctan of 0 is 0, and the limit as L approaches infinity of arctan of L is pi over 2. Now let's look at the second type of improper integrals. That is when you have discontinuity at or within the bounds. The approach is similar. If you have discontinuity at the left, then we replace the left bound by some other value, say L, and take the limit as L approaches A from the right. In mathematical notation, this integral is limit as L approaches A, and we use a small plus sign to denote that we are taking the right-sided limit. So the limit as L approaches A from the right of the integral f of x evaluated from L to B. Similarly with the discontinuity at the right bound. For example, here we have integral of f of x evaluated from A to B, and the vertical asymptote occurs at x equals to B. So here we are going to replace B by some other value, for example, r. And we are going to take the limit as r approaches B from the left. So the limit as r approaches B from the left of integral of f of x evaluated from A to r. Now let's look at some examples. The first one, we have integral of 1 over x evaluated from 0 to 1. This function has a vertical asymptote at x equals to 0. So this integral has discontinuity at the left bound. And using the approach, we are going to replace the left bound by some other value. And we are going to take the limit as the value L approaches 0 from the right of the integral 1 over x evaluated from L to 1, which equals to limit as L approaches 0 from the right of 1 of x evaluated from L to 1. That is limit as L approaches 0 from the right of 1 of 1, which is 0, minus 1 of L. And remember that line function looks like this. As x approaches 0 from the right, the y value goes to negative infinity. So the limit as L approaches 0 from the right of negative 1 of L is infinity. So this integral diverges. Now let's look at the second example. Here we have integral of 1 over x squared evaluated from negative 1 to 1. This function has vertical asymptote at x equals to 0, which is within the bound. So here we are going to use the properties of integrals to rewrite this as integral of 1 over x squared evaluated from negative 1 to 0 plus the same integral but evaluated from 0 to 1. So now we have two improper integrals with discontinuity at the bound. The first integral we have discontinuity at the right bound, and the second integral we have discontinuity at the left bound. So we can rewrite this as limit as r approaches 0 from the left of integral of 1 over x squared evaluated from negative 1 to r plus limit as L approaches 0 from the right of the integral 1 over x squared evaluated from L to 1, which equals to limit as r approaches 0 from the left of negative 1 over x evaluated from negative 1 to r plus limit as L approaches 0 from the right of negative 1 over x evaluated from L to 1. which equals to limit as r approaches 0 from the left of negative 1 over r minus 1 plus limit as L approaches 0 from the right of negative 1 plus 1 over L. This term, as R approaches 0 from the left, it means we have a very small negative value. With the negative in front, this term is positive infinity. And this term, we have 1 over a very small positive value. So this term is also positive infinity. So we have infinity plus infinity minus 2. Then the minus 2 is negligible. So this limit equals to infinity. So again, this integral diverges. And that is the end of the video. If you are interested in learning more Calculus 2, I'll put the link to my online course down below. If you like my video, please like and subscribe, and I'll see you in the next video.